Today we start talking about maximization and minimization. In fact, the great mathematician Euler had once remarked that nothing in this universe goes on without something being maximized or minimized. So, this is a very important topic, a subject which is also close to my heart, and so we are going to really talk about what do I mean by a minimum and minimizer. Now, there are two types of minimum concepts. One is a global minimizer, one is a local minimizer. For example, if you take the function y equal to x square. So, this function y equal to x square, which is basically a well known function, and all of you have studied it very well during your undergraduate your high school days. So, at x equal to 0, the function value is 0 and rest it is non-negative. So, x element of R is a global mean or global minimum or global minimizer, I would say, if fy is greater than or equal to fx for all x in R. We are now talking of functions from R to R, and we will soon be talking about those functions which are also differentiable. So, now what is a local minimizer? Means a minimizer which need not be satisfying this definition for all y, but for some y which are very near x. Let me have a look at this one. So, now what happens is that look at this function. Now, here look at this particular point. So, let us call this as the point x. Now, if look at this point which we call this as the point z, the function value at the point z is obviously less than the function value at x. So, what we have is f of z is strictly less than f of x. So, which means that f of x is not minimizing the function over whole of R. So, what does it do? But there seems to be a valley. So, valley talks about a minimizer, a mountain, hill, summit talks about a maximizer, which you can form your definition maximizer exactly in the similar way, only changing the signs. So, this implies that x is not a global minimizer. So, we call these points minimizer, and the functional value at that point has a minimum value. For a global minimum, we say the function fx value at fx is a global minimum value of the function. We do not really talk about local minimum values. So, we just talk about the local minimizer. So, x naught is not a global minimizer. So, when you are going to talk about some points near y, let us look at a neighborhood around x. So, this neighborhood, say I say x plus delta and x minus delta. Then what happens if you observe that for all y that is lying in this neighborhood, this open set, we have that f of x is less than or equal to f of y. So, this is called a global a local minimizer. So, x is a local minimizer. But there has been an interesting concept called strict local minimizer, which actually tends to alleviate situations where a local maximizer you can look at you can have a problem whose global maximizer may appear as a local minimizer to you. For example, if we let us look at a function of this form. Now you take point x equal to 0, then you can easily see it is the global maximizer of this function. But if you take a small neighborhood around it, then the function value is equal, everything is equal to 0. So it does satisfy this definition of a local minimizer. So in this case, some people can mistake x equal to 0 as a local minimizer, which it is by definition, but its more important and intrinsic property is that it is a global maximizer. So to alleviate this sort of problems, there is this notion of strict local minimizer. Loc means local. So it says that for all there would exist some delta. So this delta is, you have to show such a existence of a delta, right, that okay, you can find some delta and you can construct that interval. So you can find again a delta such that for all y, look, x is also in this interval, all y in this, but y not equal to x, f of x is strictly less than f of y. Then we call a strict local minimizer. For example, here x equal to 0 is actually a strict global minimizer. So there is no chance of this sort of anomalies. So when you have this concept. Now how do I characterize a minimizing point if the function is differentiable? That is the next question, because we tend to work more with differentiable functions. What we have not shown you, but we will show in the exercise, that every differentiable function is continuous, but every continuous function need not be differentiable. This is something you keep in your head, you keep on repeating in your head, and you should be able to tell this to anyone even if you are blindfolded under a shower. So now, so if I have f from R to R and x be a local minimizer, and f differentiable, I am writing for short DIFF, does x satisfy certain character, a certain property? We can show that f dash x would always be equal to 0. But f dash x equal to 0, so this is, so if you have a minimizer, if you guarantee to me that this given point x is a minimizer, local minimizer, then that we can always guarantee that this will happen. But we cannot make the reverse guarantee that if this sort of thing happens, that f dash x equal to 0, I will get back a local minimizer. For example, you take the function f x equal to x cube. So first to check whether a point really is a minimizer, let me first try to find out which points satisfy this. So such points, any point which satisfies this is called a critical point. And in the case of f x equal to x a cube, x bar equal to 0 is the only critical point. So for f x equal to x cube, x bar equal to 0 is the only critical point. But you see, x bar equal to 0 is not a minimizer, not the maximizer, it is just a critical point. You do not have to really bother about the fact that there is a point of inflection and the curve changes shape from concave down to convex down to convex up and all those things, forget about it. So here you have the case that f dash x equal to 0 does not translate into the fact that x is a local minimizer. So, when does it translate into the fact that x is a local minimizer? So, we have to now talk about sufficiency conditions. So, this condition that you have seen is necessary conditions, is necessary. Now, what does this mean? Let us see. What I will show is that you need additional information about the derivative of f in order to ascertain whether this given x, which you have found to satisfy f dash x equal to 0, is a local minimizer or not. You can tell a similar story for local maximizers, but I am just keeping myself to local minimizers. Possibly I am comfortable with it, but people can also, economists for example, would try to think in terms of maximizers. So, here it is very important for people in economics, this part, and of course in engineering. So, here let us look at this case very well. Now, if f, so now I calculate at the critical point the second order derivative, the second derivative, and if this is greater than 0, then we say this implies that x bar is a strict local minimizer. So, this is a very interesting and wonderful fact which seems to give you a huge amount of information. So, let us just take up an example, very simple one, a quadratic function. But it might be a laughable thing to those who know convex analysis or convexity, but those who do not know about it, it is something interesting and we will follow this method. So, we want to find, so my question is to minimize f(x). So, how do you minimize it? So, my first step will be to know, are there any critical points, because every minimizer has to be a critical point. Suppose there is no critical point, there is no question of minimizer. Every minimizer is a local minimizer is a critical point. So, if there is nothing, no point is a critical point, then there cannot be minimizer. If a point is not a critical point, then it cannot be a local minimizer. So, let us find the critical point by taking the derivative of this. So, derivative of this is 4x plus 1 and that is equal to 0. So, that would imply that x bar for example is equal to minus 1/4. Now, I would tend to, so the only possible critical point is this one. Now, let us see what is f double dash x. F double dash x here is 4. So, it does not matter whatever be your choice of x, f double dash is 4. So, which means f double dash minus 1/4 is also 4 and that is strictly greater than 0. That would imply that x bar equal to minus 1/4 is a strict local minimizer. In this case it is global, but I would not go into the explanation of those things. It is a strict local minimizer. Does every function have only one local minimizer or one global minimizer and only one point which can satisfy the global minimizer? No. For example, you take f(x) is equal to sin x, and I want to find at which points this has a minimizer, local, global, whatever. So, the function values are of sine is if we are taking x in radians, then it is varying between +1 and -1. So, what happens? So, and I know that what are the points where you have +1 and what are the points where you have -1. So, what are the points, or you can also try out this example later on, if x is equal to cos x. So, what are the points where you have f to be +1 and f to be -1. this is pi by 2, this is pi, this is 3 pi by 2, of course this is again come back to 0 in 2 pi, and then 2 pi plus another phase of pi by 2. So, you know what is it, 5 pi by 2. So, if you know, and similarly, so the points, so what are the points of maximizer and what are the points of minimizer? Here it will be again 3 pi plus pi by 2. So, 3 pi plus pi by 2 would be, so pi 0 pi 2 pi 3 pi, and 3 pi plus pi by 2 would be 7 pi by 2. So, let's look at the position. So, the global maximizing value is 1, global maximum value, and global minimum value is -1. So, now if I take the set of solutions, that is the minimizers, then that exactly equals to what? What would be the minimizers? They would be of the form x, such that x is equal to so if you of course, so you have infinite such minimizers now, countable in fact, n equal to 0, that gives you 3 pi by 2, n equal to 1, that gives you 5 pi by 2. So, n equal to, so if you take the next minimizer, it is 7 pi by 2. So, see how we do the math. So, if I do, I have to put 5 here. So, or so we are doing some experiment. Suppose we had put 2n plus, now okay, we say okay 2n plus 5, let us see, will this work? So, I put n equal to 1, I put n equal to 0, then I have of course 5 pi by 2. You see, so this thing is not working. So, what should I do? Let me just try out 2n plus 1, and to try out this I have n equal to 1, I take the odd numbers, n equal to 3, n equal to 5 and so on. So, if I put n equal to 1 and I am getting 3 pi by 2, n equal to 3 I am getting 7 pi by 2 and so on. So, these are the points of global minimizers. So, these are global minimizing points. So, now, but now if you want to have f double dash x, sorry f dash x of this, you have to have your function will be cos of x. So, you have to find cos of x equal to 0. So, you have to find a solution to this equation. But for cos of x equal to 0 does not mean that each and every point would be a minimizer. So, you then have to take f double dash x, and that will give you minus sine of x. So, you have to see for what x among the solutions of this equation, for what x this value would become strictly positive, then you take it as a minimum maximizer. What x, if this value f double dash x becomes strictly less than 0, then it becomes a maximizer. So, it has to be very careful that there can be many points which are local minimizers and global minimizers. So, that is a very important idea. But it is not that every function that I give you will have sort of minimizer or maximizer. For you just saw f x equal to x cube. So, you take for example, a function which is increasing, it is a strictly increasing function. if you look at to draw a tangent to these curves, this functional curve or the graph of the function at any point, and if you look at the tangent of this, the slope of this tangent where we calculate tan alpha, and you know that from your high school that this slope is nothing but the derivative. So, then you would see that when f is strictly increasing, so we do not actually have a minimizer in this case, it just goes up or goes down. For example, so if we take a linear function which is strictly increasing, let us see what happens. Suppose I take a linear function f x is equal to 2x, then you see f dash x is strictly bigger than 0 because f dash x is equal to 2. So, you cannot find a maximizer or minimizer of linear functions. So, this is something which you also have to keep in mind. So, with this I am closing my discussion of maximization and minimization. This is a very short discussion. Now, for example, you can try out this f x equal to tan x. Can you find sets of maximizers and minimizers? Can you find in the next talk we are going to talk about a magical thing called the mean value theorem. We are going to give a lot of examples of how powerful that notion is, and that also comes by using the derivative. What we are trying to do, once we know the function is differentiable, we are trying to approximate the function value at a given point using its derivative at some point nearby, and that is a fundamental tool of calculus which you really have to know. The idea of the next talk is following. If you have information about the derivative and if you want to know something about the function, you have to use what is called a mean value theorem, and that is what we will harp on in the next talk. Thank you very much.